And so this will essentially, today we'll close out Unit 2 mostly. We'll have some stuff to say on Thursday, but not a lot. I'm sure we won't have a snow day this week. So, now that we're back, any questions on anything before we charge off? Administrative questions about the exam? Okay. So, we left off, we started looking at the Laplace equivalent circuits. And essentially, we're talking about impedance now. And we went through all this, so this will be a bit of a review, and you can find things online, our slides, other people's slides, whatever the case may be. We have our time domain circuit, and then our Laplace equivalent. And a resistor is just a resistor in either domain. And again, a quick reminder, Z means impedance, so we'll use that a lot over the remaining semester. So Z means impedance, and then the subscript R for resistance. And we had a capacitor, and in the Laplace domain, a capacitor was a capacitor and an initial condition term. So this was VC 0 minus over S, and this is 1 over SC equals ZC. So the impedance of the capacitance. And a quick reminder here, if this is the voltage across our capacitor as the function of time, this is the equivalent voltage, VC of S. So these are 1 to 1, and that includes the initial condition term. Now everything becomes a little bit more trivial when the initial conditions are 0, of course, but the more complete situation. We could add VR and T here, which is just, again, the simpler scenario. And then we have the inductor. And we did this all before break, but it's been a while. VLT. And the thing to remind yourself of here is the initial condition source is inverted in some sense. All these are assuming current going down. So we could add a current here, current here, current here as well. That's following our polarity convention, where we assume current goes from the positive to the negative. Now these are transient circuits, so that doesn't hold the case anymore. If we look at power, power still depends on which way current is going relative to the voltage. So we can have an inductor charging up, so to speak, in which case it's a power sink, or an inductor acting like the source, discharging, in which case it's a power source. But we're not really going to look at power in this part of the course, but it's something to remind ourselves of. And this is a ZL equals SL, and then an LIL 0 minus. And VC 0 minus equals VC 0 plus. And again, this could be any time. We use 0 frequently as a reference because it's an easy reference. But whatever our initial condition is, if we define at 100 seconds or 5 minutes or whatever the case may be, it's just the continuity condition for the time you're talking about. So these were our tools that we use in the S domain. And so, if you recall, we had a little kind of procedure here to analyze circuits or Laplace analysis. What we wanted to do was find the initial conditions. And we had to do that in differential analysis as well. So this is not dissimilar. But you need to find the initial conditions to find the Laplace equivalent circuit. Determine Laplace equivalent circuit. And once you have the Laplace equivalent circuit, you can use circuit reduction concepts or any of our Unit 1 concepts. Use Unit 1 concepts. Node analysis, MASH, voltage dividers, all that stuff, etc. To find an expression for our parameter of interest. So a little bit longer step, but at least to write out. In terms of impedances. So just like we did in Unit 1, we found things in terms of resistances if we did symbolic analysis. We can do that here in terms of impedances. And remember, this is going to be a function in some sense. It's going to be a function of S. And so S is a variable. So we see that here. There's not hard and fast numbers now. We have this variable term S. It's going to be in this expression. And as a sub-step here, we want to make sure our expression is of polynomial order in the numerator and the denominator. So these are polynomials. So in some sense, when we get this impedance expression, we need to clean it up. And that's where, kind of the tedium takes place, and I'm sure maybe some of you have already experienced that. When you try to manipulate things to get polynomials in the numerator and the denominator. It's easy to screw up, but it is just algebra. So step-by-step algebra, no problem. Once you get it in this order, find the poles. And as a subtopic, zeros, but not relevant. This is going to wind up being Unit 3 more than anything else. But as long as we're finding the poles, we may as well find the zeros at the same time. Once we find the poles, partial fraction expansion. And I guess we can add a little subtopic here. We use the cover-up rule, or whatever technique we want to apply for coefficients. And then inverse Laplace transform. Minus 1, and that gives us time domain response. And so these are the steps we want to follow. So that pretty much summarizes the last part of our Unit 2 material. And we did that, I think, a little bit quickly, but maybe not yet. And we talked about these steps. So, what's that? So these are the things we want to go through. And so we can use a nice, simple example. Is anybody still writing?
Yes.
Hold off a second before we do a simple example. So we've done kind of all these steps individually, and we haven't put them together yet. So we've seen partial fraction expansion, we've done inverse Laplace transforms, we saw poles and zeros, we looked at the pole-zero plot, looked at the physical interpretation of what the sign of the poles means, talked about the left half plane. At the end of class, we did look at the Laplace equivalent circuit. We did set up a simple transfer function. Okay? So if we look at a circuit, and we're going to go back to one of our old friends, the source, R and C. And so if we look at this circuit, well, here's our time domain circuit. Remember, that's a function of time, even it's a step function. It turns on at t equals 0, so it's a function of time. And so if we look at this, well, there's our time domain circuit. And what's our Laplace equivalent? Well, it's the Laplace transform of the source, whatever that may be. It's going to be some function. For a step function source, it's a constant over S, and that's largely what we'll look at when we look at problems by hand. Because as we mentioned, those are easier to solve. We know the impedance of the resistor, ZR equals R. And we know the impedance of the capacitor, ZC is 1 over SC. And then we have an initial condition source here as well. So there's our equivalent circuit with our Laplace transform of the source and our initial condition. And again, to remind ourselves, that's VR of S, and in total, that's VC of S, which corresponds to VR of T and VC of T. And so, as we look, well, if we want to find an expression for VC of S, how do we do that? Well, in some sense, we can write VC of S equals VZC, to write it like that, plus VC 0 minus over S, right? That's the source, the initial condition source term, plus the voltage drop across that ZC impedance. The voltage drop across this guy. So here's our initial condition source term. And then voltage across only the ZC term. So those are in series, and if we're looking at voltages, we can add voltages in series. And as I've said already a couple times, voltage across the capacitor is both those components. So we add that. Well, this is fine as it is. VC 0 minus is going to be some number. You find it with the initial conditions, whatever those are. Could be 0, depends on what the circuit is. And then this is the voltage across this guy. Well, how do you find the voltage across this guy? We talked about this before break. How do you find it? Just the voltage across that component. What type of circuit is that? It's a voltage divider. So VZC, then, and here I can write of S if I want, though a lot of times I drop that. But that's 1 over SC. I can leave it a little bit more symbolic for the moment. ZC over ZC plus ZR times, well, we have two sources in series, V source of S minus VC 0 minus over S. And the minus sign comes out because of the polarity declaration. So we don't know the sign of this, of course, but if it was plus minus, they would have opposite polarities, and they would subtract, as we just showed right here. Then we can add now our ZC, which is 1 over SC, 1 over SC plus R, source of S, minus 0 minus of S, over S, I should say. And now this is not quite in polynomial form, so we want to clean that up. We have a 1 over S and a 1 over S in our numerator and denominator, not a polynomial. Multiply everything by S over R. So if you want S over R times S over R, and you wind up with 1 over RC, S plus 1 over RC, V source of S, minus VC 0 minus of S, over S, and all of that VC of S equals. And essentially that's kind of a boxable concept right now. If we have an RC circuit, we now have an expression for the voltage across the capacitor in the S domain. So from here on out, it's what we did last week. We find the poles and partial fraction expansion. Did I just screw something up? Is that okay? Oh yes, at the end, right. So that was everything. Is that why you guys have that? Right. Plus the initial condition at the top. So, now, to come back for a second, a little thing that we said here, we wanted to get polynomial form. The addition of polynomial forms works as well. So if you have an expression, this is already in polynomial form by itself. This is n of x over 2x. You can do the inverse Laplace transform of this naturally. So if you break this down for a second, and this will save you some aggravation of trying to get one big, huge fraction or whatever that looks a little bit more messy. We could write this as just some capital F of s plus g of x, where f is, it's unfortunate, that guy, and g of s is that guy. You could write it like that. When you take the inverse Laplace transform, so Laplace minus 1 of dc of s, which we know was dc of t, winds up being f of t plus g of t, whatever the Laplace transform is that. Well, this Laplace transform we're very familiar with. So you don't have to combine everything if you already have it in a convenient form. So you can leave terms out like this. So you can look at these individually and take the Laplace transforms of them individually. Now, most likely some things will cancel out. You'll get some terms that have the same exponential argument. But there's no reason to combine everything to get a single ns over ds. You can have multiple forms of this. And that's fine. But anyway, put that aside for a second. So once we have this, this is where the circuit analysis comes into play. From here on out, it goes back to math. Whether you're familiar with Laplace transforms or not, whether you saw them in differential equations or not, doesn't matter. You can do partial fraction expansion, and you probably saw that somewhere in high school or something like that. You can apply that, you can go to the Laplace table, look up the transforms of the partial fraction expansion, and get it into the time domain. So you don't need to be familiar with the math behind it, just use it as a tool. So, let's look at a couple examples here for a second. Some of these things we can do by inspection. In the first order circuit, Laplace is not any better. Arguably, you could say it's a little bit more tedious than doing it with a differential equation, but that's all right. So there's our circuit, and we want to find dc of t. So if we go back to our steps, find our initial conditions. What are our initial conditions here? Something we want to be able to recognize quickly. What are our initial conditions when there's a step function source? 0. Equals 0. So that already makes things a little bit easier. If we go back to this expression, well, 0 and 0, those guys go away. That's nice. And so, well, there's our initial conditions. Find that IC is what's supposed to be in there. 2, Laplace circuit. This is from the steps I've written a minute ago. So what do we have here? That's still 1K. And because our initial condition source is 0, if you want, you can draw it in here as a short since it's 0. You can write 1 over 2 times 10 to the minus 6. S. Or 5 times 10 to the 5. S over S. And then this is 5 over S. That's the Laplace transform of the step function. We saw that a lot. Again, that's one you don't want to be able to do off the top of your head. U of t by over s. Well, as an aside, before we dive in, maybe it's possible we can just write the differential solution of this. Anybody know what that is by inspection? Does that look right?
Yes.
You should be able to do that. So there's our goal. Here's our check result. So it's been a couple weeks, and we're going to want to be able to do that before next week. So we already have an expression, find expression for BC of S. That was step 3. And we've already done that, BC of S in this case, because we have, excuse me, 0 initial conditions. Well, here's our form. We could write this out in a little bit of detail. This way. 500 over S plus 500. That's 1 over RC. 5 over S. And if we want for completeness, we can write minus 0 plus 0. Just for kicks and giggles. And so we wind up with 2500 over S plus 500. Right? No problem. Find our poles and zeros. Well, in this case, the poles jump out at us. S equals 0. S equals minus 500. Why the minus sign again? The minus sign corresponds to stability. We want our poles to be negative or at 0. At 0 is okay as well. So we want them to be in the left-hand plane. If we had a positive pole, we'd be in trouble because it would grow in an unstable manner. So there's our poles. We can do some partial fraction expansion. 2500 over S plus 500 is going to be A1 over S plus A2 over S plus 500. I hope we're all in agreement. There's the partial fraction expansion. Apply the cover-up rule, multiply both sides by S, evaluate at S equals 0, and you get A1 equals 5. And similarly, you're going to get A2 equals minus 5. Does anybody want to see that, or do you believe me? Everybody comfortable with that? So there's our partial fraction expansion. This is fairly straightforward. Oops. So now we have BC of S equals 5 over S plus a minus 5 over S plus 500. And we do the inverse Laplace transform. Of all that. And we get 5 minus 5 e to the minus 500t, which was the same thing I had just written down a moment ago. Wherever that went. So 1 over 2 times 10 to the minus 3 is 500. Check it on your calculator. Make sure I did that math correctly, but feel good. So it checks. And that's good news when both our approaches mean the same thing. Now again, arguably, Laplace domain, not any advantage here. And even in second order circuits, if you're comfortable with those differential equations, maybe not much of an advantage there as well. But as you go off and study communications or more sophisticated concepts, it will be a big advantage, and you'll see it. Okay. Everybody feel good about what we just did?
So we should not write the UT
This is for t greater than 0, so that's a good point. I mean, the more complete mathematical solution is for t greater than 0. These are all solutions for t greater than 0. Sometimes I forget just to write it down, but it's implied. All our solutions are for t greater than 0. That's a good point. But Laplace is, when you do Laplace analysis, it is for t greater than 0, so it always is in there. Now we can look at a comparable situation. Is anybody still writing anything? So same circuit, different initial conditions. And so there's our time domain circuit. Well, what's different about this circuit? Well, we have 5u of minus t. What is that equivalent to? When we write that, 5u of minus t, that's the source being on since the beginning of time and turning off at t equals 0. And since it's a constant for that period of time, what can we say about the capacitor? It is certainly fully charged. And so we have Vc 0 minus equals Vc 0 plus equals 5 volts. And so what is our Laplace equivalent circuit now? Well, our source is off. So remember, this is a t greater than 0 circuit. And so there's our Laplace equivalent circuit. And we know what these values are, so we can write them down. So, now what do we do? Well, again, we go back to our expression that we've already solved. May as well take advantage of it. Once again, there's our solution for the voltage across the capacitor in the S domain. In this case now, this term is 0 and this term is non-zero. So we can go ahead and write out what our Vc of S is. Put our circuit back up. So we wind up with 500 over S plus 500. And our source is 0, so we can just add that. Minus 5 over S plus 5 over X. Remember, that's V source of S, which in this case it turned off, so for t greater than 0, our source is 0. This guy is Vc 0 minus over S. And this guy also Vc 0 minus over S. And that's 1 over RC and 1 over RC. And so we can write this out again, 2500 over, excuse me, S plus 500 plus 5 over S. And this is where I said you don't have to really get one fraction. This is fine. You can have multiple fractions. If you're hardcore, you could multiply things out. You could, if you want. Not necessarily recommended, but if you want, you could write this as 2500 over S times S plus 500 plus 5S plus 500. I don't know. Gives you something to do on a Friday night. They have the same denominator. And then so you could add them together and get a single numerator and a single denominator. Not needed. So if we just work out this, well, we already, yeah.
Is it negative 2500 over 500?
Oh, thanks. Yeah. So we've already done this expression. We already found the coefficients and everything here. So just to shortcut some work, this winds up being minus 5 over s plus 5 over s plus 500 plus 5 over s. So there's the first term, there's the second term, and sure enough, as luck would have it, these guys cancel each other out. 5 over s plus 500, and that gives us a VC of t equals minus 5 e to the minus 500t. Which, if we check, winds up being the same thing as minus 5 e to the minus t over rc. Oops, not minus. The minus kick there. Which would be consistent with the capacitor discharging in an RC circuit. So again, we've seen that expression before. So those are pluses. And so that would check. And so first order circuits, again, not particularly any advantage doing Laplace or differentials. Hopefully you can do them quickly in either direction. So everybody good with that? Any questions on that? Exciting stuff to come back from spring break and do. Well, before we look at second order circuits, let's go look at some old friends for a moment. Something else to remind ourselves of. Let's draw the circuit correctly. So we looked at this circuit a few weeks ago. There was this particular type of circuit. Does anybody remember what it was? Yeah, it's one of those. Let's find out. Well, arguably, in the Laplace domain, if we do the Laplace equivalent, you could just draw these as boxes. And this is what you could do in some sense all along. So our impedances can be boxes. And these can be functions of s. So it doesn't just have to be R1 over SC. It could be some expression NS over DS or whatever the case may be. In this case, we'll call them Z1 and Z2. And that's V out, and that's V in. And if this looks familiar, well, then you need to hang a little ground off the plus sign. If that looks familiar, it should look like our inverting amp error. And so impedances and resistances are comparable. And so we can say this is just V out minus Z2 over Z1 times V in. And that was accurate. That was true. And so, well, Z2 in this case was 1 over SC. That's the impedance of the capacitor, and Z1 was R. In this case, fairly straightforward. But there could be more circuitry in there, but there's not this time. And so we can write this as minus 1 over SC over R times Dn. And rewrite that a little bit. 1 over RCS times Dn. And again, this is all in the Laplace domain. I didn't write them, but these are both functions of s. And again, we're neglecting some initial conditions here. So we're assuming 0 initial conditions. So we want to take the inverse Laplace transform of that, V out of s. So brackets, inverse Laplace transform. And so, well, the inverse Laplace transform of V out of s is just V out of t. And that's the definition of the inverse Laplace transform. R and C are constants. Minus 1 over RC And we have the inverse Laplace transform of 1 over s times Vn of s. Well, if you go to the Laplace table, which I did not bring, but perhaps you still have in your notes, but what's the inverse Laplace transform of 1 over s times a function of s? What is that equivalent to? The inverse Laplace transform of 1 over s is a step function. That's true. But I'm asking for one of the combined. Neglecting initial conditions. Yeah.
Use that in the last page for a second.
What's that?
Can I think of the last page?
Oh, I'll put it back in a second. So I'm just asking, does anybody remember what that is? It's the integral. So that's equivalent. 1 over s is equivalent to an integral when you do the inverse Laplace transform. And likewise, Laplace transform of s before spring grid. So what do we have here? Dn of t. So we have that 1 over s term times Vn of s. You take the inverse Laplace transform of that, and that's the integral of Vn of t. And lo and behold, if you go back on your notes 4 weeks or so ago, we can recall that was the integrator. And we derived that using relationships between current and voltage of capacitors and resistors. But here we did it with the math. So using impedances and known relationships for Laplace transforms. Is that okay now? Did you get it? On the same token, what's this going to be? Well, we know what it is by symmetry. It is the differentiator, but we can prove it to ourselves. That's a Z2 equals R. That's a Z1 equals 1 over SC. And so V out equals minus R over 1 over SC, which equals minus RCS. Oops, there's the V in there. V in, take the inverse Laplace of that. So again, these are of S, and sure enough, V out of T, like we just said a moment ago, dV in by dt. So when we take the inverse Laplace transform of S times V in of S, we get the derivative. We're going to do it that way. So everything that we did for the past 3 weeks or so, we can do all in the Laplace domain. Well, let's go on to second order circuits. Let's look at the parallel RLC circuit. We haven't spent a lot of time with that, so let's look at this for a moment. For a long moment. So here's our parallel RLC circuit. There's our time domain. What is our Laplace equivalent? Well, this is just IS of S, whatever that may be. Resistor is still a resistor, of course. The inductor with an initial condition term. Minus plus. L, I, L, 0 minus, and that's SL. Our capacitor, 1 over SC, plus minus, BC 0 minus, over S. And so, there's our circuit. And we can find, again, anything we want in this circuit. So the voltage course, is all the same, VR of S, VL of S, and DC of S. They're still in parallel. Those are the equivalent voltages. But we can look at our classic value that we are always interested in for differential circuits. We could ask the question, IL of S equals what? Well, how are we going to analyze this? A little question mark in there. How do we find the expression? What tools do we use? What tools would you use to find IL of S? I would prefer node analysis. Does anybody disagree with that? I like node analysis. We can do node analysis. There's only one node up there. We can hang the ground off that guy. All our other nodes, we do have a node here, of course, and a node here, but if you put a ground, those nodes are constrained. It goes back to that concept we talked about in DC circuits. Relative to this ground, we know what the value of that node is. It's Li, L0 minus. Doesn't matter that there's an S in this term, but the voltage of that node, DC 0 minus over S. And so we can use node analysis. And we can write this as IL of S plus IR of S plus IC of S. And we did the same thing in the time domain. Equals I source of S. So the current through the inductor plus the current through the resistor plus the current through the capacitor has to be equal to the current through the source. Well, there's our parameter of interest, so we don't want to do anything with that. But we have this IR and IC. Well, how do we find those? Well, what's the voltage there? So if I'm doing this as node analysis, I could write this a different way. I could call this VA over R. Plus IL, in this case, I'll just write that as IL of S. We don't have to write that any differently because that's the parameter we're interested in. Plus VA minus VC 0 minus 1 over SC equals I source of S. Oh, VC over S. Is that good? Everybody okay with what I just wrote? So the current through the resistor, VA, if we want to be a little bit more complete, VA minus 0, plus the current through the inductor, which is what we're interested in, plus the current going down this direction, while the current going down that direction is VA minus the voltage here, which is VC 0 minus over S, divided by the impedance. Another way of writing all these things, all these things is VA over ZR plus ILS, which again is what we're interested in. And this is VAS as well. VAS minus VC 0 minus over S over ZC. Essentially, write it a little bit more symbolically, I would put that first only, just to remind ourselves where all that 1 over SC and all came from. Well, what's VA? In terms of our circuit, what is the voltage VA? Well, that's VL. And what's VL? Well, it is LDI, LDT, but in terms of this circuit, what's the voltage across the inductor? So we're still going for our parameter of interest. So this is SL times ILS, right? That's the voltage drop across this guy. That's Ohm's law, current times impedance, minus LIL 0 minus. So that's what we saw at the beginning of the class, right? That's the voltage across that inductor. The current times the impedance, in this case, because of our polarity, minus LIL 0 minus. So remember the whole thing here, that's VL of S. So where does that leave us? Well, this is where things start to get perhaps a little bit messy. SL, IL, gas, minus LIL. Is that someone's phone? That's cool. Was that the commercial? Isn't it?
Old Spice.
Old Spice, there we go. Awesome. SLILS minus LIL. 0 minus. C 0 minus. Over S. 1 over SC. And granted, this looks a little bit messy. And I won't disagree with that. But it is still just algebra. It's easy algebra to make mistakes on, but it is algebra. So no differential equations. And if we went higher order, this is a second order expression. We're familiar with that. If we went higher order, certainly more manageable in the S domain than it is in the differential domain. And so we can collect some terms. So we wind up with ILS times SL over R plus 1 plus S squared LC. There's our left-hand side. We're going to move all the source terms to the right-hand side like we've done before. There's our I source of S. There's a source term, so plus L over R, IL 0 minus. There's a source term, plus SLC, IL 0 minus. And then squeeze this in, plus C. And that was a little no, okay. So BC 0 minus and our S cancel. So there's our expression. Nice and simple. But again, these are all initial condition terms. Now the last thing we want to do here, we do want this in terms of ILS. So a little bit more rearranging here. If I do some manipulation on this, I get 1 over LC S squared plus 1 over RCS plus 1 over LC times all this stuff, which I don't feel like rewriting. And if you look at that, that would now be in a polynomial form. So every one of these terms, we have a constant on these two terms. We have an S in the numerator on this term, constant on that term. So everything's in a polynomial form. So that's it. So find the poles, find the zeros, and do the inverse Laplace transform. So that all came out of the circuit analysis. Maybe not so pretty. Maybe you're arguing that this is not a better approach. And again, I said, for first order circuits, it's a wash. For second order circuits, it may be a wash as well. If this is a zero initial condition problem, I think it's more straightforward. With initial conditions, it does get a little bit more messy algebraically, but it's still algebra, just to emphasize that point. So, and I think I stapled the pages or Xerox the pages out of order, so if we go actually to the last page of the handout, we have an example. So if our source is IS equals 5 U of t milliamps, how does that clean things up? Well, what does our circuit now look like? 5 over S, or 0.005 if you're so inclined. And so we have some values here, 0.2, 0.125, very real values. That was a little sarcastic. And then 0.5. And our initial conditions are 0. So because we have this, we can write IC are 0. And so that makes life a little bit easier. And we can go back to our nice messy expression that we just wrote out, and we can now say I L of S equals 1 over LC S squared plus 1 over RCS plus 1 over LC times I source of S. So many phone calls today. And so we can plug in values there if we do a little bit of math. If I can remember what the math was, we wind up with, that's 16, S squared plus 10S plus 16, 5 over S. And by random chance, I picked values that gave us real roots. So we can find S equals minus 2 and S equals minus 8. Do we agree? So again, I did this a little bit quickly, certainly, but in some sense, once we have it in this form, it is a solved problem. And I've talked about this with regard to our RLC series and parallel circuits before. We've solved these problems. It's not bad to just kind of write this down and have it as a reference. We'll look at these circuits again in Unit 3, and we'll be very familiar with this. That's a C, by the way. That's a C. So, partial fraction expansion, or to write this out, we have 80 over S plus 2, S plus A equals A1 over S plus A2 over S plus 2 plus A3 over S plus A. So the magic here is to get it in that form and then plug in the numbers. Now I skipped a bunch of steps because we've seen this, but is everybody comfortable with what we just wrote? At some point, redundancy gets a little bit tedious. And so if we plug in some values there, we wind up with some numbers, which I'm looking down somewhere. And you can check yourself. We wind up with 5 plus 1.667 e to the minus 8t minus 6.667 e to the minus 2t. Now there are a couple things to check here. What can we do having gotten this solution? What should we check? I mean, what should be true? There's two things we can really look at just to see if it makes sense. What should we look at? This goes back to our differential solutions. I mean, what should we look at just to see if, on a rough estimate, these results make sense? Right, so we should look at our DC steady state. And if we look at our circuit, well, at DC steady state, what happens to the inductor? We should remember it shorts, the capacitor opens, not that that's relevant in this circuit. So when the inductor shorts, we have 5 milliamps, and I should put a little milliamp there. And yeah, this is U of T as well, as was asked before. This for T greater than 0. So we know as T goes to infinity, we should get 5 milliamps across that inductor. Is that consistent with our solution? Yeah, sure it is, because as we put t goes to infinity here, this term goes to 0, this term goes to 0. What else should we check? One other thing we should look at. The other limit. What's our other limit? At t equals 0. There's our initial condition. By observation, what do we say our initial conditions are? They're 0. You plug in t equals 0 here, does that check? Well, 6.667 minus 6.667 is 0 in my book. If you disagree, we'll take it outside and talk about it later. So certainly, those answers check. Now, that doesn't mean we did everything right, but our DC steady state and our initial conditions are correct. And we would have to make sure our poles were correct as well. As a final observation, again, we have two real and negative poles. This is an overdamped circuit, and we see that in the response. And we can go ahead and look at that as well. In our expression here, omega naught squared was 16. We've derived this before, which means omega naught is 4. And 2 alpha was 10, which means alpha is 5. And alpha is greater than omega naught. And that's the condition for overdamped. All right. So, time for a team assignment, and then we'll look at some critically damped and underdamped as well. As you look at this team assignment, again, to write things a little bit more generally. IZ2 of S equals what? What type of circuit is this? The current divider. So IZ2 of S equals what? Z1 over Z1 plus Z2 times I source of S. And again, a reminder, Z1 and Z2 can be a collection of components. They're going to be a function of something. So it doesn't have to be just a capacitor. It could be a capacitor or an inductor in series, or in this case, a resistor and an inductor in series. A little clue for doing this assignment. Or minus J3. And that's okay. So our expression in this case winds up being IL of S in partial fraction expansion, A1 over S plus 4 minus J3 plus, I'll leave the numerator alone for a second. What can we say about the coefficient in the numerator? Anybody remember from before break? It is the complex conjugate. So we only need to find one of those, and then an A2 over S. Now in this particular case, you can use the cover-up rules, complex number. Do it on your calculator. Don't do it by hand unless you love doing complex numbers by hand. Not my personal recommendation, but if you're a diehard, by all means, do it. In this particular case, I found A1 minus 2.5 plus J 3.33, which means A1 conjugate. It's similar. It's not the same problem. 3.33 and then A2 equals 5 milliamps.
Oh, okay.
In that form, once you have this, a valid solution is this. And we talked about this before break. I should have perhaps reminded you, but we can write this as minus 2.5 plus J 3.33 times the exponential argument e to the minus 4 minus J3 parentheses T plus the other term minus 2.5. Switch my signs here. No, that's wrong. minus j 3.33, e to the minus 4 plus j 3t plus 5. So again, I skip some steps. That's a valid solution. It's complex, but valid. So that's fine. In order to get the measurable response, you would take the real part of that. That's something we'll do a little bit more of next unit, but that's a valid solution. If you are emotionally opposed to complex numbers in your solution, remember, this is alpha. Oops, the 3 there, and that's supposed to be outside. That's beta. So the real part of your complex root is alpha, and the complex or imaginary part of the complex root is beta. You can find a form, and I talked about this before, that looks something along the lines of a e to the minus alpha t cosine beta t plus phi plus b. There's our DC term. This is the same solution. Trigonometric form, you can walk back and forth using Euler's law, go from here to here. Remember, this was A1. A in this case, A equals 2 times the magnitude of A1. So if you find the complex coefficient there, then that A is 2 times the magnitude of A1, and phi is inverse, is the angle of A1, or in this case, tangent minus 1 of 3.33 over minus 2.5. And again, we looked at these complex numbers before break. Is anybody not sure what I wrote there? That's the angle of A1 and the magnitude of A1. Is that not familiar? Anybody not comfortable with that? This is only if you want to write it in this form. This is a valid solution. In order to get these, use your calculator, please.
Oh yeah.
I mean, here, when you find this one, you probably have to 0. This winds up being a complex conjugate, complex number times complex conjugate. So when you did that, you did a
That's what I'm saying.
this should get the remember when complex number times complex conjugation is magnitude squared. Use the cover. You have to plug in the whole. Right. Well, you want to use your calculator.
Yeah, here's the thing. I'm like, what the fuck? Walmart watch.
All right, I do have, I want to look at the critically damped case. So if you have complex poles, you're in good shape. You still do the cover-up rule with complex numbers. Use your calculator.
You have a good eraser?
You that warm? You that warm?
What?
He's about to do more lecturing.
Oh, and this was recording the whole time. I'm going to edit use the sparks out.
What do you use to edit?
Windows Movie
Oh, okay.
Maker. Yeah. I won't be able to edit tonight. I'll have to edit tomorrow based on what I work today.
Okay, let's look at our last.
We're going to be handy in those.
We looked at overdamped. We looked at underdamped.
Well, yeah, because I want to actually try to do it.
Just this guy? I mean, just to write this out a little bit more rigorously mathematically. I'll come back. So the solution generally. I'll put it back up. This is the underdamped attenuation, transient term. There are multiple ways of writing this. We said this before. Using differential analysis, we can find an equivalent circuit. Here I'll use different coefficients because I don't want to indicate they're the same. These all give the same results, provided you, of course, do it correctly. And I've mentioned this before, but each of these coefficients is, of course, different. The DC steady state term has to be the same for each, so I left that as A2. These are all different ways of writing the same thing. The complex number may be a little bit more confusing. A1 and A1 conjugate here are complex numbers. So in this case, B1 and B2, if we do this using differential method, these are real numbers, and then this is a real number. In this case, A is 2 times the magnitude of A1, where that's A and that's A1. So the vertical bars means magnitude of. A quick reminder, if A1 is a complex number, we did this before break, but I guess it's worth writing down again. A1 equals A real plus J, A imaginary. If there's A real there, there's A imaginary, then that's A real plus J, A imaginary on the real imaginary axis. The length of this line is the magnitude of A. It's a different A, or A1, I suppose I should write. And the angle here, that's phi, and phi is tangent minus 1 of angle imaginary over angle real. And that comes out of whatever 9th grade trigonometry or whenever you take those classes. One thing to be careful of here, and this is worth pointing out because we'll run into this in the next unit. As far as the inverse tangent in your calculator is concerned, what's the difference between these two? So this would be minus AR minus J A imaginary. As far as your calculator is concerned, what's the result going to be? And I heard someone say it. They're the same. So one thing to be careful of when you do angles, in this unit I don't care, you can leave it in that complex form. In some sense it's safer. But next unit we will care. In order to correctly do angles, make sure you know what quadrant you're in. So that does matter. This is a little bit of an aside, not something that's extremely pertinent unless you really want to go through trigonometry and prove these to yourself. Not something I'll discourage, but again, math home on a Saturday night, always good stuff to do. I do want to look at the critically damped case before we break for the day. Go off to say hello to all your friends. So again, similar circuit, no initial conditions. It makes life a little bit easier. IL of S, once again, nothing's changed. 1 over LC, it's a C S squared plus 1 over RCS plus 1 over LC times I source of S, Laplace form. In this particular case, we have numbers, we can do stuff out, and wind up with something that looks like 16 over S squared plus 8S plus 16 4 over S. We can find our poles. We have a pole at S equals 0, and minus 4, a double pole. And hopefully we're all on the same page. That does work out. And so what do we wind up with? Well, IL of S equals A1 over S plus 4 plus A2 over S plus 4 squared. We saw this before break again as well. And A3 over S. And we can go and do the cover-up rule for what? We can do the cover-up rule to find A3. Find A2. But we cannot use the cover-up rule to find A1. Right? We saw that before break. So how do we find A1? Well, all this cover-up rule, it's kind of a math trick. What we have here are 3 coefficients. Arguably, what we could do is we could just plug in values for S, plug those same values in this expression, so we wind up with 64. Or no, sorry, 80. That was supposed to be 5. So we can plug in any number for S, any 3 different numbers for S, and get a linear system, right? That's got to work. Plug in S equals 1, S equals 2, S equals 3. As long as your calculator order or accuracy is sufficient, that will work. And for poles like these, it will work. You can plug in S equals 0, 1, 2, 3, get 3 equations, solve a 3 by 3 matrix, get A1, A2, and A3 without using the cover-up rule, and maybe feel better about ourselves. Once we know A2 and A3 using the cover-up rule, though, what can we do? Essentially, you have one equation and one unknown. It turns out in this case, A3 is 5 and A2 is minus 20, so essentially we have A1 over S plus 4 minus 20 over S plus 4 squared plus 5 over S equals 80 over S plus 4 squared. How do we find A1? Well, there's the down and dirty easy way. Plug in a number for S and find A1. It's got to satisfy that equation. You have to be careful, though. There are 2 numbers you cannot use. What are they? The poles. So you cannot use, here we used S equals 0, here we used S equals minus 4. So I don't know, put in S equals 1. Plug in, find A1. That's valid. A1 then winds up being minus 5. And so that's an approach. There's another method called the residue theorem, using differential approaches. This is fun. I can show you that next week or next Thursday because I already owe you 2 minutes.